To explain Lagrange multipliers, we will be using a common example known as the milkmaid problem. So pretty much we have a milkmaid who needs to get to the river and then to her cow in the shortest distance. This river models a complex function we'll know as gx. So pretty much the milkmaid has to minimize the distance from where she is to the river and then back to her cow for any point along the river. So the function that we will be minimizing is known as fx and equals mp plus pc. The distance from one focal point on an ellipse to a point on the ellipse to the second focal point is always the same. So we want to find the smallest ellipse that has a tangent point with the river. Since we know that this point runs tangent to the river and the ellipse, we know that this point will make the shortest distance between MP and PC. And also, since this point is both tangent to the river and the ellipse, so we know that the normal tangent vector of f of x and g of x have the same direction, which means that the gradient vector of f of x is equal to the gradient vector of g of x times some unknown number, which is called lambda. And that is the basis behind Lagrange multipliers.
So one example of using the Lagrange multipliers is finding the max and min values of f of xy equals xy on the ellipse x squared over 8 plus y squared over 2 equals 1. The first thing that we should notice in any Lagrange multiplier problem is that if there are two equations, one of them is always the constraint. That is the one equal to the integer value. The other one is the function that you are trying to maximize or minimize. After recognizing which equation is the constraint, the Lagrange multiplier equation must be set up. Since each equation is a function of two variables, each gradient vector will have two components. When you take the gradient vector of the first function, you'll get y comma x, and when you take the gradient vector of the second function, you'll get x over 4 and y. Since there are three variables you have to solve for, x, y, and lambda, you need three equations. Two of them can be found by breaking down the components of the Lagrange equation, and the third is simply the constraint. The next step in solving this problem is just algebra. There are a lot of different ways to do this, but the way that you can see is being done right now is equation 2 is being plugged in as x to equation 1, and it is being solved for lambda. Once it is found that lambda equals 2, equation 2 is plugged into equation 3 as x, with lambda as 2, and then you can solve for x and y. Now we can see that there are two possible values for y and x, but we don't know which ones are the maxes or mins. To figure out which is which, we just need to find the function values at each value of x and each value of y. The easiest way to do this is to set up a table where you have the value of x with its value of y and the function value. Once you calculate the function value for each possible point, it is easy to see which points are the maxes and which points are the mins. In this problem, you will notice that both the equations listed have integer values on the opposite side of the equal sign, which means, yes, they are both constraints. You don't have a function set up for you, but if you read it, it says plane x plus y plus z equals 1 cuts into cylinder x squared plus y squared equals 1 in an ellipse. Find the points on the ellipse closest and farthest from the origin. So what you're finding is distance. So f of xy is the distance formula, which is x squared plus y squared plus z squared, all square rooted. But if you are going to maximize the root of something, it is also to be said that you can maximize that thing without the root. So really, the equation that we're maximizing here is f of x, y, z equals x squared plus y squared plus z squared. Now we have g1 of x, y, z, g2 of x, y, z, and f of x, y, z, which is the first constraint, the second constraint, and the function. Since there are two constraints, the Lagrange multiplier equation has two parts. It is the gradient vector of f of x, y, z is equal to the gradient vector of the first constraint times lambda plus the gradient vector of the second constraint times mu. So in this setup, there are two different Lagrange multipliers, lambda and mu. Now there are 5 variables, x, y, z, lambda, and mu. So we need 5 equations. 3 of them you can get from the Lagrange multipliers, and the other 2 are the constraints. Since you now have 5 equations and 5 variables, all you need to do is solve it algebraically.